Welcome to Lecture 22, Parametric Equations. To motivate this, let's recall the vertical line test from basic calculus. A curve describes a function if no vertical line crosses it more than once. Okay, so let me ask you this. How can we describe curves where the vertical line test fails? So something like this, we know how to describe this. If this is x and this is y, you know that this graph can be written as a function, f of x. So let me give you a non-example, something that you're familiar with, something you've seen. Here's a circle. How do we describe this curve? Well, in this case, one way we could do this, so this is one answer to this question, is we could describe this as all points where x squared plus y squared equals 1. That is certainly going to work, right? But what I'm going to do is I'm going to show you a different way, and in some senses, it's probably better to say this is a better way because it's going to work for more functions. So, for example, this function here, or this expression x squared plus y squared equals 1 describes the circle. What if I took out a point? What if I took out this point right there? What if I took out that point? Now, that's not going to work anymore. There's really no way to modify this to describe a circle minus a point. So our method, which are called parametric equations, that's going to work even if we do something weird like take out a point. Okay, so to give you an introduction to parametric equations, I'm going to define them on the next slide, but let me motivate them first. Is this point, I'm going to stick with this point that I wrote. This point, let's say it's at angle t. Now you know that this is the point cosine of t, sine of t. So let's suppose now that I want to describe all points in this circle. One way to do that is I could say this circle consists of all points that can be written as cosine of t, sine of t for some number t. But I don't need to do all numbers, or I don't need to do all values of t. I just need to go between 0 and 2 pi. So suppose t is greater than or equal to 0 and less than 2 pi. So I could say that this circle is the set of all points or that can be written as cosine of t, sine of t, where 0 is less, or where t is between 0 and 2 pi. This is another valid way to describe this circle. And now you can see that if I want to remove a point, say this point at pi over 4 radians, all I have to do is I can just remove pi over 4 from here. I can just say t is between 0 and 2 pi, but not equal to pi over 4. So what we're going to do with parametric equations is I'm going to call this a function of, so cosine of t is a function of time, and sine of t is a function of time. This is the x, so think of this as describing an ant that's walking along the surface of the circle. So the ant, at any time t, this is the x-coordinate and this is the y-coordinate. So if you take all possible values of t that I specify, then the ant has traced out all points on the circle, and that describes a curve that potentially fails the vertical line test. So formally, the set of points of this xy, where x is a function of time and y is a function of time, and time is constrained to some interval, is called a parametric curve. Let's write our interval as being AB. In that case, so let me draw a picture of this first before we proceed. So maybe So right here maybe is the initial point. So so at this point, at time equals a, our ant is right here. So this is the point f of a, g of a. Now as time increases, the ant is walking along this path until finally ant at time t equals b reaches this endpoint. So let me draw that in blue. So this endpoint, the ant is here at time equals b, and this is literally, it is the point f of b, g of b. And notice there might be self-intersection. So there could be points where there could be places that fail the vertical line test. There's no reason the ant can't do something like this little s. There could be points of intersection, something like this. The ant could be at this point at multiple times. So usually, if we know which direction the ant is moving, then we might draw a line like this just to indicate the direction. Okay, so what do I want to say about this? So t is, this is called a parametric equation because x and y depend on a single parameter t. So x and y depend on a single parameter. That should be a g, single parameter t. So t is called a parameter. I usually think of it as time. And often, so probably the most common way to write this is something like x equals f of t, y equals g of t, and then t might be in some interval, say a, b. And we'll just write it like this. One of the important things, probably the last thing I'm going to say on this slide, is that there could be many ways to parameterize a curve. Parameterization is not unique. For example, there are many ways an ant could start here at time A and end here at time B, or even any other times, and trace along this path. Maybe the ant goes along here at a constant speed. Maybe he goes really fast and then slows down, like a tortoise and a hare thing. Maybe he goes here and he goes around this thing 5 times and comes back down. From the underlying curve, the underlying curve is just the footprint without the parameter. There are infinitely many possible parameterizations. For example, let's take the unit circle. One way to parameterize this is, as we've x equals cosine of t, y equals sine of t, and t is in the interval 0 to 2 pi. That is one way to parameterize the circle. In this example, the ant is going to start and end right here, and the ant goes around counterclockwise. Well, let me give you another one. Oh, I forgot my end bracket. Okay, so here's another example of a parameterization. I'm going to use blue now. What if I use x equals cosine of 2t and y equals, just to be fun, negative sine of 2t, and t is in 0 to 2 pi. In this case, the ant starts here, but now goes in that direction and goes around twice as fast. In fact, the ant goes around clockwise 2 times in this interval. And there's no reason I need to start at 0 and end at 2 pi. I could go from 0 to 1. For example, here's another one. I'm just making these up on the spot. X equals cosine of pi t. Y equals sine of pi t. And t is in 0, 1. In this example, the ant starts here, goes around counterclockwise, but goes around faster. It only takes the ant 1 unit of time to go around rather than 2 pi. And that's because instead of cosine of t, I have cosine of pi t. So there are many ways to describe parameterizations. I don't even have to do continuous functions. And well, for our examples, these will all be continuous. But in theory, you don't need to make these things continuous to have it describe a parametric equation. Let's do an example and have one that's a little less obvious than the sine and cosine ones we've been doing. So graph this set of parametric equations. And it should not at all be obvious what this thing looks like. And in general, there isn't really one surefire way to solve any of these. It's like integration. You might be able to integrate it, you might not. I could give you really complicated functions for x and y, and in general, there's no good way to know what the graph is. Unless you go into your calculator and you go into parametric mode. This is something that, if you're like me, you probably discovered this when you were bored and not paying attention in high school math, and you realize your TI 80, for me it was 85, now it's probably 92 or something. You go in your TI 82 and you realize there's a parametric mode, and you don't know what this means, so you plug in a whole bunch of random things and see what happens, and you would get these weird looking curves, and that's exactly what this is. So here's one. You go into your TI 92 and you plug in parametric mode, you type in this for x and this for y, what's it going to spit out? And the computer can do this. We can't always do it, but the ones I give you, you'll be able to. Okay, so how do we do this? Let's start with the first equation, x equals t minus 2. So one thing is, if we can always solve for t, in this case, t equals x plus 2, then we can plug that into the second equation, and now we have a standard equation, x is a function of y. So let's do that. So basically what we're doing is these first two equations have 3 variables, and yeah, that's right. There are 2 equations with 3 variables. So if we can eliminate the variable t, now we have something in Cartesian coordinates. Okay, so we've solved for t. Let's eliminate it. So now let's sub back into equation 2. And if we do that, we get y equals negative x plus 2 squared plus x plus 2 plus 1. Let's simplify that. That is, I'm just going to be careful. Negative x squared minus 4x minus 4 plus x plus, and then I'm going to combine this 2 and this 3 to be plus 3. So this is negative x squared minus 3x, and then I have minus 1. And can I factor that? I should be able to. Or actually, no, I don't think I can. Okay, so I don't know how that factors. I do have it on my computer, graphed. So if you actually graph that, what you will get is you will get a parabola that looks like something like this. What's the initial? Okay, so actually, be careful. That parabola, that is what this is, but we're only doing this for time greater than 0. So, well, let's see what point, or let's see where the ant is at time equals 0. So at time equals 0, at t equals 0, where's our our hero, the ant, is, so the x, well, I'm going to say x equals, how about that? So time equals 0, x equals 0 minus 2 is negative 2. Y equals negative, I don't need to say that. Let's just say, well, sure. 0 squared plus 0, I feel dumb writing this, plus 1. I could have just written 1. So at this point, or at time equals 0, our ant is at the point negative 2, 1. And since I've actually graphed this ahead of time, I know that that point is right there, negative 2, 1. Yeah, I can write that better. Sorry. Okay, so at time equals 0, negative 2, 1. Okay, so this is where the ant starts. What direction does he move as time gets larger? So what you could do if you wanted to, you could plug in time equals 1. Let's just for fun, let's do that. We don't have to, but at time equals 1, x equals 1 minus 2, negative 1, and y equals negative 1 squared plus 1 plus 1, that's equal to 1, I think, yeah, 1. So at time equals 1, our ant is here. So this is, how do I want to write this? T equals 0, and this happens at t equals 1. So our ant, notice, looking at the x-coordinate, the ant is going to move in the positive x direction. So as t gets larger, x gets larger linearly at the same rate. So our ant is going to be moving in a constant speed in the x direction. So we didn't actually need this point to know the ant was going in this direction. So the ant is moving in this direction at a constant speed, but in the vertical direction, its speed is increasing quadratically. So what's going on is the ant starts here, and then the ant walks along this path, and it speeds up in such a way that its x direction, that the speed in the x direction is constant, which means it has to be moving faster and faster and faster because this thing is getting steeper and steeper and steeper. So our ant starts here, and it travels along this parabola. Okay, so here's another example. X is 4 cosine and y is 2 sine of t. Now here, this thing looks circle-ish, so it's probably going to be a circle ellipse, or I don't know, something like that. It may not be an entire circle or ellipse, because we're only going from 0 to pi. But let's. So how do we approach this? So let's not actually do it, but let's talk about doing what we did in the previous problem. So in the previous problem, I looked at this and I said we had 2 equations and 3 unknowns, so we can solve for t and plug it back in the other one, and then we're set. So let's yeah, just for fun, let's do that. So solving for t in the first one is going to get you t equals inverse cosine of x over 4. And we plug that in the second one, then we get y equals 2 sine of t equals 2 sine of inverse cosine of x over 4. Okay, so y is a function of x. That is a function of x, but it's something you've probably never seen, and it's probably, yeah, and it's not going to be fun. And also, it's not clear that this is going to be true for all x and all y, because again, if this thing is a circle that wraps around a few times, at some point it's not going to pass the vertical line test, and something's going to go wrong here. So this is not the preferred way to do this problem. Instead, I'm going to use so for most of these problems, ones where you cannot just solve for t and plug it back in like the previous one, you're going to use the identity. So we're going to use the identity cosine squared of t plus sine squared of t equals 1. So we're going to use this. How do we use it? So what do we have? So we have x equals 4 cosine of t. So let's solve for cosine of t. So let's cosine of t equals x over 4. Similarly, y equals 2 sine of t. So sine of t equals y over 2. So I'm going to circle this. Cosine of t plus sine of t. Let's plug that back in. So how do I want to write this? Put this cosine squared of t plus sine squared of t equals x over 4 squared plus y over 2 squared equals 1. And let me circle that in blue. So, oh yeah, I'll put that, I can simplify that here. So what is this? This is x squared over 16 plus y squared over 2, over 4 equals 1. This is the equation of an ellipse. So this is an ellipse. This is an ellipse. I always forget how to spell this. I-S-P-E, I think that's right. This is an ellipse centered at 0, 0. Hopefully you remember your pre-calculus. With a big radius. I know there's a name for this, major, minor, something like that. Big, I think, is far superior. Big radius, r equals 4. And small radius, little r equals 2. And one of these is along the x-axis, one of these is along the y-axis. And what you're probably thinking now is, well, I don't remember too much. I don't remember my pre-calculus enough to know which is which. Well, fortunately, the great thing about math is if you forget something, you can rederive it. Okay, so let's see how to do that. Okay, so let me draw the xy. So this is x, and this is y. Okay, so our ellipse is it's either going to be something like this or something like this. So what is the largest x value on this ellipse? So let's go back up here. What is the largest value of x that I can plug in and have this equation be satisfied? Or said differently, if we're on the x-axis, then y equals 0. So let's plug in y. Yeah, this is better. Plug in y equals 0. That goes away, and x squared equals 16. So this ellipse is going to intersect, go through that point. Similarly, it's going to go through that point. And then what about on the y-axis? On the y-axis, x is going to be 0. That goes away, and y squared equals 4. So y equals 2. So this is 2, and this is negative 2. So our ellipse is going to look something like this. I can draw that better. Try that again. So this ellipse is going to look, well, not that much better, but bear with me. I think that's fine. Okay, so this is the underlying ellipse. Now, let's be careful. This parametric curve, I didn't say just go over the whole ellipse. I said walk along the ellipse from time equals 0 to time equals pi. Okay, so what does that mean? So let's plug in time equals 0. So what do I want to do this? How about this? At time equals 0, x equals 4 times cosine of 0, which is 1, and y equals, oh, how about this? 4 cosine of 0, which equals 4, and y is 4 sine of 0, which is 0. So at time equals 0, our ant is right here. Our hero begins on the x-axis. Okay, so this is the initial. Let me just call it that because that's what I called it in the previous slide. Okay, so what about the terminal point? Where's the ant at time t equals pi? So at t equals pi, do the same thing again. X equals 4 cosine of pi, which is 4 times -1, which is -4. And I'm running out of room here. I'm just going to say y, well, let's see, y equals, yeah, I'll do this here. Y equals 2 sine of pi, which is 0. So our hero ends at this point. This is t equals pi, and this is the terminal point. Okay, so next question. How does the ant get from here to here? Does it go that way? Does it go that way? Or does it do something else? Does it go around 5 times? Well, that's probably not the answer, but so how do we figure this out? Okay, so let's see where the ant was at time pi over 2. So at t equals pi over 2, our halfway point, x is 4 cosine of pi over 2, which is 0. That's not helpful. It says it's somewhere, well, I guess it's a little helpful. It says that we are either here or there. Let's see what y is. Y equals 4 sine of pi over 2. Sine of pi over 2 is equal to 1, so that's equal to 4. So now we know halfway through, t equals pi over 2. This is a halfway point. So our ant is starting at t equals, at this point, traveling this direction, traveling that direction. I think the book calls this, says a particle. I think an ant is much better visual than a particle. Okay, so our path, in summary, our parametric equation is this path right here. Starts there, ends there. Okay, so we've seen how parametric equations can describe many curves that cannot be written as functions, but it's natural to ask if we lose anything. Are there any functions that exist that cannot be written using parametric equations? And the answer is no. So I'll show you a quick way, a simple way to parameterize any function of x. So let me take a function. Say this is y equals x squared plus 1. So we can parameterize just by letting x equal t. You always let x equal t. I mean, you don't have to, but it will always work if you let x equal t. And then y is f of t. So basically we just plug t in for that. So y equals t squared plus 1. It's supposed to be a t squared. Oh god, now I just made it worse. Try that again. T squared plus 1. And then t can be anything. So you don't have to, but if you want to, you can set t to be in this range. So what's happening is that At time t, your ant is at position t in the x direction. So at time 0, the ant's going to be, so here's 1, here's 2, say. At time 0, the ant has to be right there. At time 1, the ant has to be here. At time 2, the ant has to be up here, and so forth. So, and the fact that y equals our function f of t forces the ant to be along this curve for all time t. Okay, so let's do another example. So here I'm going to draw a line segment, and I'm going to ask you how to parameterize it. So let's find of the following segment. So let me draw a point here. This is going to be the point -1, -3. And let me draw a point here. This is going to be the point 4, 1. Okay, so I have not specified anything about the path. All I'm saying is that our ant is going to trace along this path. He could start here, he could start there, he could start somewhere else. Let's make things simple. Let's suppose our ant starts here and walks to here at a constant direction. In that case, the x-coordinate is going to be increasing at a constant speed, and the y-coordinate will be increasing at a constant speed. In other words, x and y will both be linear functions. So, I'm going to say x is x naught plus a times t, y equals y naught plus b times t. So x and y are both linear functions. And again, at this point I have not specified what direction the ant is walking, but let's suppose, let's just say that at time equals 0, he puts them here, at time equals 1, he's there. And I have that choice. You can't stop me from saying that. So when t equals 0, I'm going to choose an initial point. How about, so first of all, notice when time equals 0, both of these things go away. So the initial point is staring at you in the face right here, x naught, y naught. So, because again, plugging in 0, these things both go away. So when t equals 0, choose an initial point. X naught equals -1, and y equals y naught equals -3. Okay, so in other words, if we say that our ant starts right here, that forces this to be -1 and that to be -3. So now x equals -1 plus a t, and y equals -3 plus bt. You can probably guess where we're going from here. We're going to plug in another point and figure out what a and b are. Okay, so how long does it take the ant to go from here to here? It's up to us. We could say it takes them, let's see, this is 1, 2, 3, 4, 5. We could say 5 units of time or 4 units of time or something else. Let's make it 1. Let's just say it goes from here to here in unit time. Okay? So, so let's, how do I want to say this? We'll choose choose 4, 1 to be the terminal point. And let's say, and say, our ant is there at t equals 1. So at time 1, our ant reaches the other point. Okay, so let's do that. So I'm going to use red now to so let's plug in time equals 1, or let's plug in t equals 1 into here and in there, and that will tell us what a and b are. So now x equals -1 plus a, and y equals -3 plus b. See how easy it was when I chose t equals 1? I could have put something else in, but... oh, and I should say x, we chose 4, 1, so that has to be 4, and that has to be 1. So now you can see that a equals 5, b equals 4. So x equals -1 plus 5t, y equals -3 plus 4t, and I should specify that t ranges from 0 to 1. So here is our final answer. This is our parametric equations that describe the ant starting from here at time equals 1, or time equals 0, ending here at time equals 1, and going along in that direction. Okay, now that we've defined parametric equations and seen some examples, let's talk about derivatives. So the derivative of think of the ant walking along a path, the derivative should be its speed in some sense. Okay, so what does it mean for a parametric equation to be differentiable? It's differentiable at a time t if both f and g, these are the individual functions, are differentiable. So remember that x, so here x equals f of t, and g equals, I'm sorry, not g, y, y equals g of t. Okay, so in this case, let's suppose f is differentiable. In that case, by the chain rule, dy dx times dx dt equals dy dt. And this is by the chain rule. So, so assuming that this is non-zero, we can solve for dy dx. So let's write that down. If dx dt is non-zero, we can solve for dy dx, and we can get that, let me just say this, we can solve for dy dx and say it's just dy dt over dx dt. So this is the first derivative. So this is, in other words, what you think of as y prime of x. Let's take a moment to think about what this means. So if okay, so when is, oh, how do I want to say this? Yeah, so let's think of our curve as being the path of an ant. This right here is going to be the velocity in the x direction. This is going to be the velocity in the y direction. So this is literally how fast is the ant moving in the x direction, and how fast is the ant moving in the y direction. So that this is the velocity in the y direction. So, okay, so when is this derivative, when is the velocity in the x direction 0? So suppose your ant is moving along. What's going to cause that to be 0? Notice that if he ever has to turn around, go backwards, there's going to be that sum. Let's draw a picture now. If the ant ever has to turn around, going this way, go that way, that there's going to be some point in time at that point right there where the velocity, where the ant was traveling in a positive velocity, then now he's going a negative velocity. So there's some point here where his instantaneous velocity in the x with respect to x is 0. And yes, that is precisely when when dy dx does not exist, namely because dy dx, the slope is infinity. So hopefully with this picture you have a little, so the chain rule tells you that this cannot exist when this is 0, but matches up with the picture that this is 0 precisely when, well, I don't want to say precisely because there's other cases. Our bug could just stop if you wanted to. But assuming our bug or ant is moving gracefully and not stopping, that's going to happen exactly when there's when the tangent line is vertical. Okay, so let's talk about the second derivative briefly. Okay, so let's suppose that the second derivative exists. I'll show you how to come up with a formula for it. So let's write that down. Let's say that y double prime of x exists. I'll show you how to write it similar to what we did above. So then, oh, also let me just mention that d squared y, so this is what I'll show you how to do. I'll tell you what this is. But something you probably have noticed by now is that when we write the second derivative, we have a squared between the d and the y, and we have one after the dx. And for years when I learned calculus, I never understood why that was, and I finally had to figure it out. So instead of making you figure out years later, let me tell you where it comes from. So that comes from literally this. So you can think of the derivative as being an operator. So the second derivative is just this. So the first derivative is just this d dx of y, and the second derivative is d dx of y. And so now you can see nicely why we like to write this as d squared, or as d squared then y, and here in the bottom this dx sticks together, so it's dx squared. Okay, so to derive, so we want to know what this is. To do this, we just look back at the chain rule. So this formula, I've used a bunch of different colors, so let me box it in black. So we can use the same formula, but instead of plugging in y, let's plug in y prime. So by the chain rule, so by the chain rule, d, whatever we put here, say y prime, where that's dy dx. So dy prime over dx times dx dt equals dy prime over dt. And here, I should say that y prime is, I'm saying this is dy dx. I have to be careful because I've also talked about a dy dt in here as well. And so by y prime, this is just short for dy dx. And again, this formula works for y for any function. It could be y, it could be z, it could be anything else. So, same thing as before. If dx over dt is 0, then dy prime over dx, which is really d squared y. It's the second x derivative of y, is just d y prime over dt over dx over dt. And if you prefer, that is d squared y over dt over dx dt. Okay, so here is the formula for the second derivative. Okay, so let's do a quick example. So find the first and second derivatives of the following parametric equations. Okay, so one of these is quick and easy. Dy dt is clearly equal to negative sine of t. Let's do dx dt first, or next, dx dt. So the derivative of natural log is 1 over natural log of x is 1 over x, so the derivative of the natural log of this creature is 1 over that creature, by the chain rule. So 1 over secant of t plus tangent times the derivative of that creature. So that is the derivative, I believe, is derivative of secant is secant t times tangent, and then the derivative of tangent is secant squared, and then finally the derivative of sine is cosine, so minus cosine. Let's simplify this a little bit. This is, I hope this simplifies. Oh yeah, good, it will. So the top of this fraction is secant of t. I can factor out a secant of t. Tangent of t plus secant of t. And the bottom is going to be secant of t plus tangent. So now I'm going to put parentheses around this and notice that these things both cancel. Minus cosine of t. So this is, let's see, this is 1 over cosine of t minus cosine of t. That's going to simplify to 1 minus cosine squared of t. I'm going to combine those fractions like that, okay? And now I can write this as sine squared of t over cosine of t. So that is dx dt. So I wish I had written this a little smaller so I could give myself a little more room, but let's see what let's try to fit it in. So dy dt, sorry, not dy, I'll do this in blue. So dy dx, so, well, let me finish this first, then I'll say something about it. So dy dx is negative sine of t over over positive sine squared of t over cosine of t. Notice this here is dy dt over dx dt. Maybe I should have said that. So that this is I'll put this here. This is dy dt, and this here, of course, is just dx dt. This is dx dt. So let's simplify that. This thing simplifies. The signs will see. We'll have a negative cosine t on top and sine t on the bottom, and that's equal to negative cotangent of t. So this is the first derivative. Said differently, this parametric equation is a curve. I don't know what that curve looks like. I'm going to make it up. It's probably going to be wrong. Let's let me sketch it. Let's just, who knows? Suppose it is something like that. This curve. So this is x and this is y. And let's suppose that our ant starts here and goes in that direction. So at every point on this curve, let's say there, where the tangent line is not vertical would mean that the derivative is not defined. Every point where the tangent line is not vertical, we can compute the slope of the tangent line. We know what that is conceptually. That slope, whether we're here or whether we're here, at any time t, that slope is equal to the negative cotangent of t. And I think that's pretty remarkable that we can, just from knowing the path, and even though there's infinitely many paths we could choose, just from knowing the path, we are able to recover functions about, or information about the derivative and the slope of the tangent line for the original curve. Okay, so that's the first derivative. The second derivative, I hope I have room to do it here. Actually, I have another slide. Let's summarize what we got on the previous slide. So dy dt equals negative sine of t, dx dt equals sine squared of t over cosine of t, and finally dy dx equals negative cotangent of t. So we got those. And then finally, recall that the second derivative, d squared y over dx squared, that was dy prime over dt over dx over dt. Remember, y prime was dy dx. So in other words, this is, if you want to write this out, specifically this is ddt of dy dx over dx dt. Okay, so I know lots of d's and x's and t's, y's floating around, but we should have enough information to solve this pretty quickly. So the the derivative. So this is the derivative of negative cotangent of t. Is that correct? Yeah, that should be negative cotangent, and then I think that's secant I think that's cosecant squared. And on the bottom, it should be sine squared of t over cosine t. So again, this thing is just coming from that right here. Okay, so the derivative of negative cotangent of t is cosecant squared of t. And then on the bottom, it's sine squared of t over cosine of t. So this is, what is this? This is 1 over sine squared of t on the top, and sine squared of t over cosine of t on the bottom, and that is cosine of t on top, and sine to the 4th of t on the bottom, and this is the second derivative. So again, I have no idea what this function looks like. I mean, it's going to be some curve. Who knows what it looks like? But I am able to tell you at any point, or given this path along this curve, our ant travels this direction, I'm able to tell you the slope of the tangent line at any point in time, as long as that tangent line is not vertical, in which case, well, I guess I know the slope. It's infinite. Okay, so that's the end of the lecture.